The exploration of the Jovian system, constituted by Jupiter and its natural satellites, is of prime interest for present and upcoming spacecraft missions. In a way, this archetypal planetary system constitutes a miniature of the solar system and of other unachievable exosystems. The laboratory project presented in this movie focuses on Jupiter's internal dynamics. These are of crucial interest as they set the whole planetary environment, including the giant magnetosphere. Within these, an incredible diversity of celestial bodies and potentially certain forms of life are enclosed. Unfortunately, despite being the nearest gas planet from Earth, the internal dynamics of Jupiter are poorly constrained from present observations. On the contrary, Jupiter's zonal winds, recorded here by the Voyager spacecraft mission, have been observed for centuries and are well known of a large public. These large-scale dynamical jets are unmistakable markers of powerful internal dynamics, inaccessible to direct measurements. Today, understanding how these zonal winds interact with planetary interiors and how energy is transferred through gas planet envelopes is a major challenge for a vast community of astrophysicists and planetologists. Furthermore, the self-organization of large-scale, coherent flows is ubiquitous in nature. It represents an essential, cutting-edge research topic in fundamental fluid dynamics, as well as in geophysics and planetary sciences. How do these jets form and stabilize? How deep do they extend within the planet? These are long-lived conundrums in planetary science. Over the last decades, two models for explaining these prevalent features of planetary dynamics have been continuously challenged. On the one hand, you have the shallow layer model, schematically represented on the left of this cartoon. In this model, the fluid dynamics responsible for zonal winds are confined within the shallow troposphere, this being usually called the weather layer. On the other hand, in the deep layer model, to the right here, the winds invade the entire molecular envelope that exists above the deeper dynamo region. To synthesize, in natural settings, zonal winds develop from rapidly rotating flows in the presence of strong boundary curvature, which is due to spherical geometries. In particular, in physics, we argue that jets emerge when the Coriolis force, being relative to planetary rotation, dominates over inertial forces, relative to the flow velocity. These, in turn, dominate the viscous effects, which dissipate energy in the system. In addition, the flow must undergo the effect of planetary curvature. All these ingredients are required to create a system in which strong zonal winds spontaneously emerge. However, this can occur following both the deep layer and the shallow layer scenarios. Here, we chose to go along with the assumptions of the deep layer model. We have developed a new laboratory experimental device that is capable of generating strong Jupiter-like zonal jets following this deep layer model. The working fluid is water. It is contained in a cylindrical tank, a meter in diameter and more than a meter high. Once equilibrium is reached, at a rotation rate of 75 rotations per minute, the water's free surface takes the shape of a paraboloid. This mimics planetary curvature. Observe, on the left-hand side of the video, the vertical blue lines in the cut of a planet. Now compare these with the analogous lines on the right-hand side cartoon, representing the laboratory setup. Clearly, the surface curvature emulates the variation in fluid depth from the pole, the center of the tank in the experiment, to lower latitudes, mimicked by the shape of the fluid at the edge of the tank. In order to obtain jets, we now need to inject kinetic energy into our system. This is achieved by pumping water through a lattice of injectors at the bottom of the tank. You can see this as a rotating jacuzzi. This experiment is called Jovian jets in a jacuzzi. Now, how do we observe this jacuzzi? Well, look at the eye on the cartoon. It corresponds to a camera mounted at the top of a rotating frame. Let's move to the laboratory. Now we are in the lab. with our rotating device spinning at 75 RPM. We are in the IRFE Institute in Marseille. The camera that you can see mounted on the top of the rotating frame corresponds to the eye that you saw in the last image. This is used to record flow motion of the free paraboloidal surface. The hope is that we'll observe zonal winds, comparable to Jupiter's observable surface. Let's move deeper into the experiment. We are now looking through the camera in the moving frame of reference, spinning at 75 revolutions per minute. We are looking vertically down onto the paraboloidal surface. The center of the frame corresponds to the center of the cylindrical tank, i.e. the planetary pole. At the edges, we inject black ink. This ink is rapidly advected in the azimuthal direction by the zonal jets. These large-scale phenomena dominating the flow inhibit radial transport. What you see is a multiple Jupiter-like jet system. For the very first time, this flow pattern has been reproduced in a laboratory. Now, let's go further. In the new implementation of the experiment, we designed a device emulating, in the laboratory, a giant planet. Instead of a paraboloidal surface geometry, a plastic hemisphere constrained the flow to a spherical geometry. Apart from the change in the geometry, the device remains the same as the one seen in the previous experiment. Simply look at the eye. You can now imagine it as a spacecraft orbiting the planet. Now observe this new movie. Again, it is recorded by a camera in the rotating frame of reference. From our imaginary spacecraft, we are orbiting a giant planet. And, similarly to what would happen on Jupiter, we clearly observe that the flow is dominated by zonal motion around the rotation axis. You can see that large vortices develop. If we rotated even faster, we'd probably observe stronger winds damping the smaller vortices, as it is the case on Jupiter. Only the long-lived Jupiter Great Red Spot, a strong and stable vortex, remains to be explained by these laboratory experiments. This represents exciting and interesting perspectives for further experimentation.